Yes, good morning.
Good morning, sir.
Good morning. Okay, thank you. Now, in the previous class, uh, yesterday, we discussed the implementation part for implementing the binary search tree, how to create the binary search tree, and then the implementation part for traversing the binary search tree recursively using in-order approach, pre-order approach, and post-order approach. These are few things what we understood in the yesterday's class. So now today, so I have this thing. So this is again important types of binary tree. So till now we were discussing the binary tree. I hope all of you can see my screen.
Yes, sir.
Okay. So binary tree. Why it's called a binary tree? Because every node, or in other words, an internal node, can have at most two child nodes. Okay. See, when I say a tree, I can go for building a tree where a node has more than two child nodes also. But it's called binary tree here because so a node, see what you're observing here, a node can have at most two child. Okay, this then has two child, 20 and 30. So that is what binary tree, hence they are called as binary trees. Now, what are the different types of binary trees? And this question was asked many a times. Okay, you can see here, and it was asked for 10 marks. So we have a complete binary tree. So what you're seeing here is a complete binary tree. Why it's a complete binary tree? Because it is fully balanced. So if you just look into this, okay, you can see there root node and till the last level or till the leaf nodes, it is completely balanced. Okay, say for example, I said binary tree, a node can have maximum two child nodes. Okay, now here, say for example, for this node 70, if I delete this node 96, so then you can't call it as a complete binary tree. Okay, it is a binary tree but not a complete binary tree. Okay, so if you look into the definition, okay, a complete binary tree is a full binary tree in which all leaves are at the same depth. You can just observe here. So all the leaves are at the same depth. That means every node except this leaf node, every node has got how many child nodes? Two other child nodes. Okay, and it is a complete tree, complete binary tree. Okay, so this is at the level 0, this is at the level 1, and this is the level 2, and this is at the level 3. All the leaf nodes which are at level 3, all leaf nodes are present at level 3. Okay, say, so that is what is the binary trees. The total number of nodes in the complete binary tree are, how many nodes are there? So it is 2 raised to h plus 1 minus 1, where h is the height of the tree. Okay, now h is the height of the tree, and you can find the total number of nodes in any complete binary tree by using this formula. Okay, so 2 to the power h, 2 to the power h plus 1 minus 1, where h is the height of the tree. Now what is the height of this particular tree, the example tree which is shown over here? So this is 0 at level, this is first level, this is second level, and this is third level. Okay, now height of this binary tree is 3. Okay, now you can just observe here. So the height of the above given tree h is 3, so height of this tree is 3. Now if I just substitute this 3 in the place of h, 2 raised to 3 plus 1 minus 1, that is 2 raised to 4 minus 1, so 15 nodes are there. Okay, now if you are starting the level of the tree from 0, if I call this at level 0, so then it is 2 raised to h plus 1 minus 1. In case now I don't start numbering this level as 0, I want to start this level by numbering as, so can you see my mouse movement also? Am I audible?
Yes, sir.
Okay, mouse movement, can you see my mouse movement?
Yes, sir.
Okay, my hand also you can see, right?
Yes, sir.
Okay, see here. If I don't want to take this as the level 0, say I want to start from level 1, I want to call this as level 1, I want to call this as level 2, this is level 3, level 4, okay. So then it is level 4, then it is 2 raised to h minus 1. So this plus 1 we don't add it. Hope you people are following. So 2 raised to h is how much? So 2 raised to h minus 1. So if you are starting from level 1. So 2 raised to h value level 1, this is level 1, level 2, level 3, level 4. H value is 4. 2 raised to h, that is 2 raised to 4 minus 1. It's still the same. Okay. So if you are starting numbering the levels from 0, then it is 2 raised to h plus 1 minus 1. If you are numbering the levels by 1, then it is just 2 raised to h minus 1. So 15 nodes are there. Okay. So that is one property of the complete binary tree. Any point of time, if you are interested in knowing how many nodes are there, total number of nodes are there in a complete binary tree, you can just find it by using this formula. So this is the formula that you'll be using if you are starting the tree level by 0. If you are starting the tree level by 1, so then it is just 2 raised to h minus 1. This plus 1 we don't do it. Okay. Now if you just count here also, so you'll find that there are 15 nodes here. So excuse me for a while. Hello sir, class ಅಲ್ಲಿ ಇದೀನಿ, ಆಮೇಲೆ ಕಾಲ್ ಮಾಡ್ಲಾ? ಮಾಡ್ತೀನಿ ಸರ್. 10ಗೆ ಮುಗಿಯುತ್ತೆ ಕ್ಲಾಸು, ನಾನೇ ಮಾಡ್ತೀನಿ ತಗೊಳ್ಳಿ ಆದಮೇಲೆ. ಓಕೆ ಓಕೆ ಸರ್. ಓಕೆ. Okay. Now how do you find the total number of leaf nodes? So the total number of leaf nodes is n is equal to 2 raised to h, where n is the number of leaf nodes and 2 raised to h. H, you know, it's already the height of the tree or the depth of the tree. Okay. Now here, so the h value, since I'm starting from the level 0, this is 0, 1, 2, 3, 2 raised to 3. Correct, right? That is nothing but 8. So you have total 8 leaf nodes in a completely balanced binary tree of depth 3 if you are starting from 0. And similarly, if you are starting from the level 1, so then the total number of leaf nodes in the complete binary tree is given by n is equal to 2 raised to h minus 1. Okay. Hope you people are following.
Yes, sir. Yes,
okay.
sir.
Okay. Now, so you understood that these are the two important properties of a complete binary tree. You understood now what is a complete binary tree is, and how to find the total number of nodes in the complete binary tree, and how to find the total number of leaves in the complete binary tree. So in both the cases, when you are starting the level from 0 and when you are starting from the level of the tree from complete binary tree from 1. Okay. So now we have an example also here. So this is actually a proof. Okay. For any non-empty binary tree, okay, so non-empty binary tree T, if n0 is the number of leaf nodes, what he is saying is, so n0 is the total number of leaf nodes, okay, and n2 the number of nodes of degree 2. n2 is the number of nodes of degree 2, then prove that n0 is equal to n2 plus 1. Okay. Now here See here, these are all the leaf nodes, and n2 is the number of nodes with the degree 2. Okay. Now if you just take this, okay, this node, the degree is 2, so we don't take into account this link, we don't count. So we count only the links which are connecting the child nodes to itself. Okay. For 40, there are two childs, 80 and 90, and these are the links which are connecting 80 and 90 to this. So now this has 2 degree, and if I take this again 20, what is the degree? 2. If I take 10 again, what is the degree? 2. If I take 30 again, what is the degree? 2. 60, 2. Okay. Now what I can say is, except the leaf node, for all other nodes, the degree is 2. Node degree is 2. Following?
Yes, sir.
Okay. Now here it says, prove that the total number of leaf nodes is equal to the n2 is the total number of nodes with the degree 2 plus 1. Okay. So just observe here, look into this, the number of leaf nodes, or in other words, so to say it in the simple terms, it is like this: the number of leaf nodes, or the total number of leaf nodes, is equal to the total number of other nodes. Okay, or I can say this leaf nodes, you can also call them as external nodes. Leaf nodes, they are also called as the external nodes, and all other nodes except the leaf nodes, we can call them as internal nodes. The total number of leaf nodes or external nodes is equal to the total number of internal nodes plus 1. Okay, so just count here. So we have already found the count of the leaf nodes. How many leaf nodes are there? 8 leaf nodes are there. 1, 2, 3, 4, 5, 6, 7, 8. 8 leaf nodes are there. Now you go for counting the total number of internal nodes excluding the leaf nodes. 1, 2, 3, 4, 5, 6, 7. I have 7 internal nodes and plus 1. Okay, 7 internal nodes plus 1 is nothing but what? 8. 8 is equal to 8. So total number of leaf node is 8, n0 is 8, and total number of internal node is how many? 7, and to that you add 1, it is, they are equal. Okay, so you got to prove that the total number of leaf nodes is equal to the total number of internal nodes plus 1. Okay, now we assume n0 is equal to external nodes. n0 is that leaf node, or you can also call them as what? External nodes. And n2 are internal nodes. So these are all your internal nodes. Hope you people are following?
Yes.
Okay. Now we have to prove that n0 is equal to n2 plus 1. Okay. n0, number of leaf node, is equal to number of internal node plus 1. Okay. Now on the basis of induction, okay, now if I assume that there is only one node, that is the root node, okay, this is the only node. Okay, now when I go for finding showing whether this is true or not, just look into this. This is the only node right now, which I can call it as a root node, or else I can also call it as what? The leaf node. Okay, so even if you look into the leaf node, so this is not taken into account. If I want to say the degree of this node, what is the degree of this node right now? 0, because it doesn't have any child. Hope people are following?
Yes, sir.
Now here, if I assume I have only one node, okay, now I can go for calling this as the root node. Okay, root node, but it doesn't have any child. Okay, now the n0, total number of external node, is how much? This is the only node right now, it is 1, is equal to, now number of n2 is nothing but what? Number of nodes of degree 2. Are there any node? Are there any node with the degree 2? No, 0.
No.
Plus 1. Correct, right? 1 is equal to 0 plus 1. It is true. Now when I checked it for the single node, now this statement showing to be true. It is true. Okay. Now we'll just continue with n is equal to 2. So sorry, n2 is equal to 1 and n0 is equal to 2. Now this is the case. Correct, right? So how many leaf nodes are there? 2 leaf nodes are there. And how many nodes are there? How many internal nodes are there? Only one node. Okay. Now even if I take this example, okay, I will look here. n0 is equal to n2 plus 1. How many leaf nodes are there? 2. 2 leaf nodes are there. Okay. And how many internal nodes with degree 2 are there? There is only one. This is the only node with degree 2. Okay. 1. n2 value is 1. n0 value is 2 and this is 1 plus 1. 1 plus 1 is 2. 2 is equal to 2 and again it is true. Okay. Now we proved it for n is equal to where we have only one node, and we proved it when n0 is equal to 2 and n2 is equal to 1. And I got to prove this works for all or any depth. Correct, right? It works for any number of leaf nodes or external nodes. Okay. Now in general, if you want to prove this, see here, when we add two external nodes, so previous external node becomes an internal node. Is that true? When we add external
Yes,
node, previous external node will become what? An internal node. See, say these two were not there. These two are not there. N2 and N3 are not there. Is this the external node? Yes. Now I'm adding N2 and N3. After I add N2 and N3, so this was an external node earlier, now converted into what? An internal node. Correct, right?
yes, sir.
Okay. Now N0 is what? N0 is the total number of what it is? A total number of external nodes or the leaf nodes. Now after I add two external nodes N2 and N3, now this N1 has become the previous external node, or else I can also call it as the internal node right now. Now N0 new, the total number of new external nodes is equal to N0 previous plus 1. Now previously, how many? This example if I take, before adding these two, this was the only external node. Yes or no? Now N0 previous will give you how much? 1. Hope people are following?
Yes, sir.
Plus 1. Okay? Plus 1. Now the total number of new external nodes after adding the external nodes is equal to total number of previous external node plus 1. Okay, and this is equal to now N0 previous. Okay, now this was the only node earlier, and now after adding this this was the only previous node, and the count of the leaf node or the external node was 1. Now after adding these two new, so this N0 previous can be written as N2 new plus 1. Correct? So this was N0 previous. Hope people are following? I think I can write and
Yes,
show you.
sir.
1 second. Now if I open it in this, I cannot write. 1 second. Let me close and open it in. One second. I'll open it in Microsoft Edge. There I can write it. Yeah. Well, if you can see now.
Yes, sir.
Okay. Observe now. Here n0 new is equal to n0 previous. So after adding these two, this node becomes n0 previous. N0 previous. Okay. So plus 1. But this n0 previous, okay, is equal to what? N2 new plus 1. Okay. Now n0 previous is equal to n2 new plus 1. Okay. So number of what is it? N2 is nothing but what? Number of internal nodes. Okay. And number of internal nodes plus 1. Okay. And this plus 1 is as it is. Okay. Now n0 new is equal to n2 new plus 1, because this n2 new is equal to n2 previous plus 1. Now, and this shows for any depth of complete binary tree, so this statement holds good. Okay. So this is about the complete binary tree. Okay. Now if it has to explain the different types of binary trees, so you got to take complete binary tree, you got to highlight, you got to say first what is complete binary tree, highlight on these 2 points, take an example for complete binary tree, and sometimes they will also ask you to prove this statement, and try to prove this by starting with n is equal to 1 node, n is equal to n0 is equal to only one node you consider root node, and then take n0 is equal to 2 and n2 is equal to 1, and go for proving it generally as shown here. Okay. Now almost the other type, almost complete binary tree. Okay. This is another type. Now what is this almost complete binary? Very close to binary, complete binary tree, but it is not completely a complete binary tree. Okay. Now when I say an almost complete binary tree, okay, it has to satisfy these two constraints. What is the first one? Each node has a left child whenever it has a right child. I hope you people understood. If there is a right
Yes, sir.
child, if there is a right child for a node, it should have what? The left child as well. That means there is always a left child, but for a left child there may not be a right child. Understood?
Yes, sir.
So every node or each node has a left child whenever it has a right child. This means that there is always a left child, but for a left child there may not be a right child. Correct? So if there is a right child, the left child should be there. And if there is a left child, so it's not necessary for you to have what? The right child. So this is one constraint. I have the example, I will show you. Next, the leaf in the tree must be present at height h or h minus 1. The leaf nodes or the external nodes, what we say, they must be there either in the level h or height h or height h minus 1, not behind that. Okay. So that means all the leaves are on two adjacent levels. The leaf should not extend above the two adjacent levels. So these are the two constraints. Hope you people you understood with the constraints.
Yes, sir.
Okay. Now look here, look here, look into these examples now. We have 3 examples here. Now just look into this first example and tell me whether it is satisfying both the constraints. So check whether each node, correct, no? The internal node, sorry, each internal node has a left child. So 10, does it have a left child? Yes. Correct, right?
Yes,
And
sir.
20 is another internal child. internal node. Does it have a left child? Yes, it has a left child. Correct? That means this first constraint is satisfied. And go for checking whether does it satisfy the constraint 2. What the constraint 2 says? All the leaf nodes must be present on 2 adjacent levels or at the height h or h minus 1. Getting? Now, say this 40, 50 and 30 are the leaf nodes, are the external nodes. And what are they present at the 2 adjacent levels?
Yes, sir.
Correct, right? Now this is almost complete binary tree. Correct? And they are present at the height h and h minus 1. This is height 0, this is height 1, and this is height 2. And that is maximum height is h value is how much? 2, and h minus 1 is what? 1. Now all the leaf nodes or the external nodes, they are present at 2 adjacent levels, that is h and h minus 1. Okay, so this is almost complete binary tree because it is satisfying both the constraints. Hope it is clear.
Yes, sir.
Yes, sir.
Okay, next look into this next example. So in this example, see here, how many internal nodes are there? How many internal nodes and how many external nodes?
2 internal, 2
Two
external.
external.
2 internal and 2 external. What are those 2 internal? 10 and 20 are the internal, 30 and 50 are the external one. Yes or no?
Yes, sir.
Now
Yes,
let us
sir.
check whether this tree satisfies the first constraint. Every node or each node has a left child whenever it has a right child. So this node 20 if I look, so 10 if I look, yeah, there is a right child and it also has a left child. Good. Now if I look into this 20, it has a right child but there is no left child. But now this condition is not satisfied. Correct, right?
Yes, sir.
Yes, sir.
Correct. And just check. So for condition 1 is not satisfied. Okay. Now we'll try to check whether the condition 2 is satisfied. Is the condition 2 satisfied? All the leaf nodes are at the adjacent levels. All the leaf
Yes,
nodes
sir.
are they at height h and h minus 1? Yes.
Yes.
It is satisfied. So second is satisfied, whereas it is not satisfying the first constraint, hence it is not an almost complete binary tree. Next, look at this third example now. So in the third example, so this is the root node, and does it have a left child? Yes, it has a left child. Correct? And what is the other internal node? 20 is another internal node. Okay. So it may or may not have this right child, but it should always have what? The left child. Is there a left child present for 20? Yes. So the first
Yes, sir.
condition is satisfied. And this is the leaf node, and it is not mandatory that it should have the left child or the right child. Leave it. Okay, first condition, this is satisfying. So this please mute. $185. USN 185, please mute. Okay. So this is satisfying the first constraint. Now we'll go for checking whether it satisfies the second constraint or not. What the second constraint says, all the external nodes should be present at the height h or h minus 1. So this is height 0, this is height 1, height 2 and height 3. Okay. Now this is one leaf node and this is another leaf node. Now are these two leaf nodes present at the two adjacent levels? Are they present at the two adjacent level at height h and h minus 1?
No, sir.
No. So
No,
this is present at the height h, whereas this is present at the ith. So this is h minus 1, and this is h minus 2. We have this leaf node present at the ith h, and this leaf node present at ith h minus 2 instead of h minus 1. Now hence again we say this is not satisfying the second constraint, hence it is all, this is also not an almost complete binary tree. Okay, so these are the two types of binary trees. So complete binary tree and almost binary tree. Sometimes what they do is, so they ask you to explain these trees, and sometimes they will give you some example graphs like this, and they'll ask you to identify which one is almost complete binary tree and which is not almost complete binary tree. Okay. Next, properties of binary trees. Okay, binary trees, you know, different types of binary trees, you know how to construct the binary tree also, you know how to traverse the binary tree also. Okay, now properties of binary trees. What is the first property of the binary tree? The binary tree maximum number of nodes at level L are 2 raised to L. Okay, now if I consider a binary tree at maximum, so at some level L, what is the maximum number of nodes it can have? So it can have 2 raised to L. So don't confuse this with this thing, the complete binary tree. So the complete binary tree, the maximum number of nodes is given by this formula, 2 raised to h plus 1 minus 1. So if you are starting the level from 0, if you are starting the level from 1, it is 2 raised to h minus 1. Okay, but now we are discussing the general properties of the binary tree. So we're not restricting it to what? Just the complete binary tree, the general talk on the binary trees. When I'm writing the properties of the binary trees, you know, so the maximum, I don't say the specific number of nodes that should be present inside the binary tree. What I say, the maximum number of nodes that can be there in a binary tree at level L is given by 2 raised to L. Okay. Now again, with the example we go. So proof by induction at 0th level. Okay. How many nodes will be there? When I say level 0, at level 0, a binary tree at level 0 will have maximum, how many nodes it should have?
1.
1 node. Because L value is 0, 2 to the power 0 is nothing but what? 1. And similarly, at level 1, a binary tree at level 1. Okay. Now, yeah, binary tree at level 1. Okay, 2 raised to 1 is equal to the maximum nodes are, this is level 0, then the maximum nodes are 1, and level 1, then the maximum nodes are 2, that is N1 and NR. These are the 2 nodes. Now, so and in general, maximum nodes at level 0 is 1, maximum node at level 1 is this, 2 into maximum number of nodes at 0, and then in general maximum node at kth level is equal to 2 into maximum number of nodes at level k minus 1. It goes like this. So in general you can say it as 2 raised to k. So this proves that the maximum number of nodes at level L are 2 raised to L. For a full binary tree with an ith h, it has these many. That we have already discussed. Okay. Now here we have a full binary tree with ith 2, 0, 1 and 2, which gives you the maximum number of nodes. How many? 7 nodes. Maximum number of nodes 7. Okay. And then here total number of nodes is equal to this. So for a binary tree, the total number of nodes at level m are 2 raised to m. In the above figure, so it was in the previous figure, okay, this figure. Total number of nodes at level 0 are 1, and level 1 are 2, and level 1 are 4. See, level 0 there is 1 node, level 2 there is, sorry, level 1 there are maximum number of nodes are 2, and level 2 the maximum number of nodes are 4. Now total number of nodes is equal to, you take the summation of all of them. Total number of nodes at level, maximum number of nodes at level 0, maximum number of nodes at level 1, maximum number of nodes at level 2, maximum number of nodes at level 3, and dash dash dash, and similarly the maximum number of nodes at level m. Or in general, so this can be written as summation of from I is equal to 0 to m, where m is the number of levels. Hope you understood?
Yes, sir.
Okay. So this says, so when level 0, the maximum number of what you can have is 1. When it is level 2, the maximum number of nodes what you can have at level 2 is 2. Okay. And why we say maximum? Because it can be less than 2 also. Because say for example I have only left child for this node, so then it is 1 node, but it cannot cross more than 2. Okay. That is the reason we say maximum. Now here, if height is equal to 0, h is equal to 0, then the total number of nodes are 1. That is the root node. If height is equal to 1, then the total number of nodes is equal to 3. So how it is 3? So maximum number of nodes at level 0 plus maximum number of nodes at level 1. 2 raised to 0 plus 2 raised to 1, that is equal to 3. Hope you understood?
Yes, sir.
Yes.
Okay. Next. And then induction hypothesis. Okay. This is another example which is here. Okay. So we understood right now two properties. One property is that the maximum number of nodes at level L are 2 raised to L. Don't confuse. Now what we are discussing in this property is the maximum number of nodes at a particular level. Okay. And the second property, it is with respect to the full binary tree or the complete binary tree, which we have already discussed, and the relevant proof for it. Okay. And this is the relevant proof for a specific level. Okay. Next, and this is the proof by inductive step also. Okay. So if we just go into this. And before that, let me check what is the third property. The total number of external nodes in the binary tree are internal node plus 1. Okay, that is external. E is external node, I is internal node. E is equal to I plus 1. It is from this. I'll show you. Yeah, here. So E is equal to, we have already understood this. Total number of external node is equal to total number of internal node plus 1. So I is the total number of internal node and E is the total number of external node, or the leaf node, and this is the internal node I. Okay. Based on this, so we have one more generalized induction proof. Okay. Now we'll just go through this. So total number of nodes, assume the total number of nodes is less than are equal to this 2 raised to h plus 1 minus 1 for a full binary tree when h is equal to k. Okay, where k is the number of levels. Okay, now a tree T has two subtrees, one is TL, left subtree, and right subtree TR. These subtrees are also full binary trees with height. So height of this left subtree is h of TL, represented as h of TL, and height of the right subtree is represented as h of TR. Okay, so now the complete tree T, the whole tree, can be represented as this. So dot product. So T is equal to TL dot TR. Now when I go for expanding this, T is equal to the total number of nodes at the left subtree plus the total number of nodes at the right subtree plus 1. Hope you people are following?
Yes, sir.
Yes, sir.
Okay. So TL plus TR, right? Now why this plus 1? Based on this. Based on the total number of external nodes is equal to what? The total number of internal nodes plus 1, something like that. Now here 1 is added for root node and T denotes the total number of nodes. Okay, so T denotes the total number of nodes and this 1 is also added. So how this 1? So from this. From this I have marked here. So E is equal to I plus 1. Okay. Okay. Now this T I can write it as total number of nodes in the left subtree plus total number of nodes in the right subtree plus 1. Okay. Now again this T is expanded here. Now this total number of nodes in the left subtree can be written as what? 2 raised to. Now how do you find the total number of nodes in the left subtree? You should know what is the height of the left subtree. Now height of the left subtree is represented as what? H of TL. 2 raised to h of TL plus 1 minus 1 plus again I am finding the total number of nodes in the right subtree by using the height of the right subtree. Height of the right subtree is represented as what? H of TR. 2 raised to h of TR plus 1 minus 1. Okay. Now when you simplify this, okay, now I am getting it as, so 2 raised to h of TL plus 1 plus 2 raised to h of TL minus 1. Okay. So and then taking 2 as the common, okay, this is what I am getting, 2 into, one second, yeah, I am taking max of these two, maximum height of what? The left subtree and the right subtree. Okay. Now 2 dot 2 to the power h of t minus 1. Now if I choose the maximum among these two, what it gives? This is the height of the left subtree and this is the height of the right subtree. If I take maximum, it gives the height of the whole tree. Okay, people are following?
Yes, sir.
So that is h of t. Okay, h of lt is nothing but the height of left subtree. H of tr is nothing but the height of the right subtree. When I take the maximum of these two, it gives you the height of the entire tree. Now t is equal to h of height of the entire t plus 1, and that is proved. Okay, so that is proved, and here is it is written the height of the entire tree is the maximum of these two. Okay, so now we have proved this also. Okay, next, the third important property of binary tree is that the total number of external nodes in the binary tree are internal node plus 1. That is E is equal to I plus 1. Okay, and the proof it was already shown, okay, here, and the same proof you can go for writing. So this proof, it's the same proof what we discussed earlier. Okay. Yeah. So only one, when there is only one node, sit pros E is equal to I plus 1, because external node is 1 and internal node is 0 plus 1. Okay. So 1 is equal to 1. So for one node it is proved, and similarly we are trying to prove it for what? E is equal to, sorry, n0 is equal to 2, and so instead of n0 let me take it as E here. E is equal to 2 and I is equal to 1. I have two external nodes and one internal node. So when I apply again, I am getting it as 2 is equal to 2. So proved for two external nodes also, and similarly for n external nodes. So when we do by applying the induction property similar to this, so same as that proof. Only thing is, instead of n0 I am taking it as E, and instead of n2 I've taken it as what? I. Okay. So it's the same proof. So any doubts still here?
No, sir.
Okay. So you got to remember the types of the binary trees and the properties of the binary. Two types of, and apart from this complete binary tree and almost complete binary tree, there is also something like skewed binary tree, and that is easy. What is a skewed binary tree? Is a tree which is in the split form. Say for example, so this is a node 1, say node 2, node 3, which is in the split form. This is one tree, and say for example 1 again, so they are not connected, 4 and something like this. The tree which is in the split form is a skewed binary tree, and we don't discuss any properties of this, that's all, but these two are important. And after that, traversal methods I have already showed you. Yeah, just look into this, and if you have any doubts somewhere here and there, please do ask me, because all these things are important, because you get repeated questions on these things. Yes. After this, yeah, we have threaded binary trees. Okay. The next topic that we are going to discuss will be the threaded binary tree, because we have already seen how to construct the binary search tree and traverse the binary search tree. The steps you know, and how to do it programmatically also you know, recursively. Next topic that we are going to discuss is threaded binary tree, and I think you have implementation of the tree traversal methods without using recursive technique also. So I'm not sure, I'll just look into the syllabus if that is also there. So that is one more thing which I need to cover. Yeah, I think we'll stop here for today, and tomorrow afternoon it's a lab tutorial session. Let me see whether I'll continue with the binary search, threaded binary tree, or to give the lab program on the trees. I'll decide. Okay, so Please mute, all of you. So 350, 43, 135, 156, 10, 16, 39, 116, 6, 134, 135, 136, 137, 138, 140, 141, 142, 143, 44, 145, 146, 147, 150,